Thanks for being here. This morning, we will focus on information extraction, and specifically in the first lecture, I will discuss one major example of information extraction from Earth observation data, which is land cover classification. Then, in the second hour, I will try and deepen a little bit on hyperspectral data, which I have just briefly mentioned, but I never talked extensively about it. So I think it could be useful for you to know a little bit more about this data and how to make profit out of it. Okay, so as I said, in the previous part of the course, we have seen what is remotely sensitive data, how you can obtain a remotely sensitive data, what are the features of such data, and how you can process the data in such a way that you can try and make the information that you're interested in to emerge and be collected more easily. Now, we are moving to the next step, which is information collection, which is how do we, after we have done all the necessary, all the needful things, now we take the next step and we get the information that our user needs. Remember the scheme that I showed you at the beginning of the course? We are now taking the last step. Obviously, the last step can be very diverse because depending on the application that you have in mind or the application for which you intend to use remotely sensitive data, there's a huge range of possible things that you can do. So obviously, it doesn't make sense to list them all. I thought it was more useful to focus on one of them, but not any one, but one which is a major stream in the use of remotely sensitive data, which is land cover classification. Okay. So what is land cover classification? What is classification in the first place? Classification means assigning each portion of the considered Earth surface to a class. Okay. What is a class? Well, this definition, if you take away considered Earth surface, it's a general definition of classification. So what does it mean to classify? I have a set of objects, and I do a classification when I take each one of these objects and I put it into a slot which represents a class, where in each class I will find objects that are similar to each other in some sense, which I have established as a criterion for classification. Okay. Now, we're simply transferring this intuitive concept to geospatial data, and we will be leveraging Earth observation data to do this task, to carry out this task. Okay, so what is classification? Classification is assigning, in this case, the object is a portion of the Earth's surface. It can be, for example, just let me rush ahead, but I think it's useful. It can be the pixel. Okay, you carry out an acquisition from a satellite, and then you take each pixel, and you assess to what class such pixel may belong, and then you put it in the corresponding group. That is classification. So, and a class is a homogeneous category selected from a predefined set. We will discuss this. More interesting to define here is the result of a classification, of this classification process, which we call a thematic map. Okay, so a thematic map is a map, regardless of whether it is an actual map or not, map in a classical sense. So it's a subset of geospatial information where for each portion of the area that I'm looking at, I can identify a class. Okay, that's a thematic map. So it's not necessarily a map in the sense that I look at it and it looks like a map. Okay, when I say thematic map, I mean the result of a classification operation, of a land cover classification operation. Okay, so thematic maps can be, now let me point this out. Thematic maps do not need satellite data in order to be produced. We have produced thematic maps for centuries without satellite data. Okay, so we are putting together two things here. We have the concept of thematic map, which is what is there, what is located there, what are the features there. We are merging it with our area of interest, which is remote sensing. Okay, so we're using remote sensing as a means to produce thematic map, but we should be aware that it's not the only possible approach. Another typical approach is, for example, in situ inspection. If you go to the place, you will see what is there, and you can mark the thematic map with the class that you have found there. Okay, and yeah, let me reiterate that what we are doing here is providing an example of information extraction from the data. So once more, we have data, and then we have information, and we need to move from data to information. Data is numbers. Information is what I need. And here I want to turn piles of numbers into the information that I am interested in. Now, let me see. And this can be done not only at the scale which you have seen here, so where we have a thematic map on practically an entire continent, where this is Corinne land cover map from 2006. It's a land cover map which covers the whole of Europe. And it basically breaks down the surface of Europe into various classes which are listed here. See? And again, even in this case, what you're looking at is not the data itself. Again, it's a visual representation of the information that was generated. Okay. Remember, I mentioned it multiple times that you should not consider remotely sensed data as images. They are not images. Okay. They are numbers. You can derive images from these numbers if you set up a certain procedure. In this case, and you get a visual representation of data. In this case, we have a visual representation of information, but information is not there. You don't use, for possible further stages of processing, you won't use this image. Okay, this is just for your use. The information has been translated into a map, which you can see and assess. But the data is hidden behind it. Okay? And the data are numbers which tell you, for example, the number of class, the order number of the class which has been assigned to that specific classification unit. Okay? Does that make sense? This is just to put things a little bit in order before we move on. Okay. And as I said, this is an example at a continental scale. So it's a very broad area. So the resolution is not very high. I think it's something like 100 meters or so. But you can also do that at a much finer scale. So we have an example here. This is not a data set. This is an image derived from a data set, but it is used to show you what type of data we are dealing with. This is our campus, actually. it's a long story. If you search for hyperspectral data, if you want to experiment with hyperspectral data, then this is the so-called Pavia data set, which has been around for several years now. It was an experiment of acquisition of hyperspectral data sets, which was done on our campus because we filed an application, it was accepted, et cetera, et cetera. Anyway, we start from hyperspectral data. And this is the visual representation. We start from hyperspectral data, and we implement a classification procedure which leads us to get a thematic map. Okay. Obviously, it doesn't matter that the pixel here is the size of 1 meter. In the other case, it's 100 meters, 1 kilometer. It's different parameters, but the concept behind it is the same. Each one of those data units has been translated into a land cover class, which is generally represented by a color for visual representation. But again, it's just visual representation. Be aware of that. Okay. Generally, in addition to the data set, as we will see, you will need a so-called training set. I think this is a concept which sounds familiar to many of you, especially those who work with deep learning. Okay, so the training set was not invented for deep learning. The concept of training set is older than deep learning in Earth observation, because the training set is used to tune the operation of the classifier even though you're not using deep learning. Okay. So in this specific case, the data set, the hyperspectral data set, is distributed along with a training set that you may use for training or tuning your classifier. So the basic concept of a classifier is an object, an algorithm, software, whatever you want to call it, which is capable of ingesting remotely sensed data of various types, meaning that the same concept applies to hyperspectral, to multispectral, to radar, to whatever type of data you can think of, or even to multiple types of data at the same time. Okay. Then, working on this data in a suitable manner, it can produce a thematic map. Okay. Now, there's one distinction to be made here. I talked about land cover. Land cover is essentially the biophysical cover of the Earth's surface. Okay, so for example, vegetation is a land cover class. Urban is a land cover class. Buildings are a land cover class. But there's also another definition which is around, and it's called land use. Land use is not a synonym for land cover. Be aware of that. Land use means the function of that land cover. Okay, so land cover is what is physically there. Land use is how is that used for. So, like for example, if you have a road and a parking spot, the physical covering, material covering the Earth's surface is the same, maybe asphalt, for example, but the land use is different because in one case it's used as a road, and the other case it's used as a parking lot. Okay, classification generally leads you to getting a land cover class. Why? Why land cover and not land use? So why is land cover more reachable than land use? It's not difficult. Yeah, let me say it in another way. It is easier to get to land cover because land cover, the physical cover of the land that you're observing, is directly linked to the response that you get when you observe it. Okay, so the observation produces information about the material, not about the use of the material. Okay, generally, when you use remotely sensed data, you get to have land cover information. Then you will probably need to add something from a different source to raise it to the level of land use. Because picking up again the example of road versus parking lot, if you look at the spectral response is the same material, same spectral response. So you cannot distinguish them based on spectral response alone. You will probably have to look at other variables. Like in this case, road versus parking lot, probably you can do without other sources, because if you have sufficiently high spatial resolution, sufficiently fine spatial resolution, you can leverage spatial information, because a road is generally a narrow strip with the same spectral response, whereas a parking lot will tend to be more larger area. Okay, so this is spatial information. Something thin versus something fat is spatial information. So if you limit yourself to using spectral information, this is where you're heading for. Then, if this additional step is not too difficult, you can probably source additional information which you hadn't used before from the same data set. Okay. But it is important to keep in mind that we have this distinction, land cover and land use. And this is also an important point to keep in mind. These are called information classes. We will see later on that there are also other types of classes which are not information classes. What does it mean, information classes? It means that they are telling you the information that you're searching. Okay, so you do this because you want to know, for example, the extent of the area which is covered by buildings. This is an information which you can extract from looking and from summing up the number of pixels that were classified as building. Okay, so this is information which is provided to you within the thematic map. Then we will see why we need to distinguish between information classes and other types of classes. Okay, so once again, these are all concepts that are not necessarily related with Earth observation or with Earth observation data. Okay, as I said, cadastral data, for example, can also represent land cover data without having been sourced from satellite data. Okay, but the point is, so the advantage, let me say, of remote sensing in this sense is that remote sensing offers you a tool to generate this type of information in a fast and cheap way. So, I mean, you can theoretically you could visit every single one of these pixels and take note of what is the land cover there. And then you would produce a land cover map, and you don't even need any training data set. But obviously, this is very expensive and time-consuming. Okay, it's very accurate. It's very accurate, but it is expensive and time-consuming. So why are we interested in using remote sensing for doing the same thing? Obviously, because it's much faster. Okay, you can get this in a matter of seconds, starting from the data. Okay. On the other hand, we should also be aware that it's faster, cheaper, and it does not reach the same level of accuracy that you could get with other methods. So if you go for in situ inspection, you will get a very accurate map. You will spend all your money, but you will get a very accurate map. If you don't need all that accuracy, so if you're ready to live with a certain percentage of error, then remote sensing gives you an opportunity to reduce enormously the cost. Okay, but it comes at a price. It comes at the price of purchasing the data, obviously. It comes at the price of setting up a classification chain, and it comes at a price especially, this is especially the point, it comes at the price of not having 100% accuracy. Because, as I said at the beginning of the course, you're doing measurements of, to generate the data, which is hidden behind this image. Okay, to generate that data, you need you need to do a measurement, a number of measurements of very weak radiation from far away. So you should expect a certain degree of error. You should expect polluted spectral responses. And so this will result into a certain level of error in the result. And so as we will see, obviously, you also want to assess to what extent you can expect errors. One more thing that I believe can be relevant here is that I started the lecture talking about classes, so assigning a classification item to a single class. This is not the only possible case. This is called hub classification. So every object can only belong to one class, but you can also use this called fuzzy classification, which means that you may have partial membership to each class. Why do you think partial membership can be useful? So, I mean, if I were, I mean, I don't want to put too much brain into it. I say, okay, obviously, I look at the image, and somewhere there will be buildings, somewhere there will be roads, somewhere there will be vegetation. Why should I care about establishing a possibility to say that a pixel is half vegetation and half urban? What is the advantage? This is a difficult question. It has two responses. One is because that's how things work, and meaning that when you have defined a pixel when your acquisition process has defined a pixel on the Earth's surface, that pixel not necessarily contains all the same line cover class. It may fall at the edge between a building and a vegetated area. And this is the first. One may say, so what? So what? What's the difference? I mean, I can live with an error. I can live with attributing all to a building. I can live with overestimating the size of the building. I don't care. After all, in some other cases, it would be underestimated, so I'm fine. The second level of response is because how will these pixels behave? How do you think these pixels will show up in the data set? If you have a pixel which falls half on a building and half on vegetation, what do you expect its spectral information to be? Mixed, yeah. That's a problem. Why should I accommodate, why should I preview, why should I plan for mixed pixels? And so go for fuzzy classification. Because I need to be able to handle cases where the spectral response is mixed, so it doesn't look like anything that I have seen in the training set. We will see this a little bit more in depth in the rest of the lecture, but the point here is if you try to force everything into a single class, may work, a single class into one class of a set, may work, may not work, okay? So we have an example here where we have membership function from 0 to 1 for every pixel. For every pixel in the classification map, you have a number expressing how much that pixel belongs to that class. And generally, the sum of all the membership function amounts to 1. Okay, so when you do classification, you do that on a so-called classification unit. The classification unit is the smallest portion of the data set on which an assignment of a class assignment is made. So one classification unit may be typically maybe a pixel, because there's nothing smaller than a pixel that I can consider separately for classification. But it can also be a local cluster, or it can be a so-called super pixel, so a group of pixels which feature the same or similar line cover classes. And so I consider them all together because I don't know. If I know they are all the same line cover class, I don't need to classify them one by one. I can simply, for example, average their response to get something more reliable. In any case, the classification unit is whatever you decide to take for classification in a single classification operation. And now there comes another important point here. How do we classify in practice? Because I have mentioned that a number of times during the course, but I never put it in this framework. How do you classify? Well, we have seen that each type of material has its own specific spectral response, right? So if we look at each classification unit, and I'm making an example, okay? It's not necessarily like this. I'm making an example in which I decided to leverage spectral information, okay? So what am I supposed to do? Well, I take each classification unit, I look at the spectral response that comes with that classification unit. For example, what I can do is I compare that spectral response with spectral responses of known material, or materials of which I know the spectral response. And if something looks similar, then the one that looks the most similar, I will assign the class, the corresponding class to the classification unit. You may remember I took the keys and the key map and I said, see, it's like when you have a spectral response like this, it's like you have a number of locks corresponding to the various materials. You insert the key and you try and turn it. If it turns, then you have found the corresponding material, right? Okay, great. Now, so the basic principle which lies behind classification is that you will find, or you will search for, and hopefully you will find analogous behaviors which can let you group the data together. Either group the data together or put the data in a class if we have a similarity with a known response. We will discuss this shortly. Okay. Now, this is where the concept of spectral classes kicks in. A few slides back, I told you land cover and land use classes are information classes, right? We call them information classes because they convey the information that you're interested in. Here, it's not written on the slide, but I am anticipating it. This is where we see the so-called spectral classes. Okay, the spectral classes are the locks that I test with the unknown key to try and attribute a class to that sample, okay, to that classification unit. Does that make sense? So if you leverage, that's the important point. So you have information classes, which is what you would like to distinguish. But then there are also so-called spectral classes, which are what can actually be distinguished because they have different responses, different spectral responses. So a spectral class is a distinct spectral behavior, okay? So what I mean, distinct spectral behavior, obviously it is difficult to define in general. I would say that a distinctive spectral behavior is when you have a spectral curve which looks like nothing else. Okay, that's a distinctive. It's this key where there are no other keys which look like this. This is distinct spectral behavior. But there are mathematical formula which let you assess the so-called separability of classes. So given a class or given a spectral behavior, you can apply, there are several in the literature, which let you assess to what extent these two classes are separable, to what extent it is easy to discriminate class A from class B. And it's called separability of class A with respect to class B. Now, let's make the connection. Why are we interested? After all, our interest is in information classes, right? By definition, we are interested in information classes. Why do we investigate spectral classes? We investigate spectral classes because we are leveraging, as a first approximation, in a first approach, we will be trying to separate, to discriminate pixel classes based on their spectral response. Does that make sense? So I can only separate two classes if they are actual spectral classes. Because if I take an information class, which, if I take a pair of information classes, like, for example, road and parking lot, these are information classes. I'm interested in them. I want to know where the road is and where the parking lot is. But the fact is, these two objects belong to the same spectral class. So likely, sooner or later, I will run into trouble because I'm trying to leverage a type of information which I don't have. Because if I try and source this information from the spectral response, I will not get it. Okay, so the separability, if I ask the separability based on spectral response, that separability will be 0. Okay. Okay. So how am I supposed to act? This is a very simple scheme which summarizes the procedure of classification. I have a data set. I have a set of classification units which I will convey to the classifier, which contains a certain number of classification rules. This is a very general scheme. And these classification rules will be the result of either sourcing example from the so-called training set, or I can also get rid of this part and say, no, just group the classification units by mutual similarity. I will discuss that shortly. What is the difference? Yes. Yeah. This one? Sorry, I missed.
Classification units.
Yes.
It is here and as well as there also.
Yeah, this is classified. This is classified. Yeah, because these are still to be classified. Then I crunch them, and something here will take a decision about what class each classification unit belongs to. Okay, so here we have classified units. And these classified units will build the classification map that I am interested in. Now, whether I want to keep this part or not determines whether I am using so-called supervised or unsupervised classification. Are you familiar with this concept? Okay. So frequently, you probably have seen both cases, supervised and unsupervised. Let's have a quick look at what is the practical difference that we find between these two. At a high level, we could say that supervised classification is a knowledge-driven approach, whereas unsupervised is a data-driven approach. What do I mean? A knowledge-driven approach means that you leverage a certain knowledge that you have about the problem to guide the classification. Whereas in a data-driven approach, it's purely the data that somehow guide their grouping. Okay. So in the first case, you need examples. So in the first case, no, it doesn't work. In the first case, you remove this branch. Say it's unsupervised. So, sorry, in the second case, you remove the branch and you say, okay, let the classification units be grouped by similarity. And then in the other case, you try and teach the classifier to distinguish the classes. And when I say teach, don't think necessarily of learning, okay? Don't think necessarily of machine learning or deep learning. Teaching means passing information that can be used for classification. Even classical classifiers need so-called training to tune their parameters. Okay, so in the case of supervised classification, we have as an output directly the classes. So since the classifier learns the classes, it will output directly a map with reporting them. In the unsupervised case, you will get anonymous classes, spectral classes, which will then have to be associated with information classes. What is the advantage of unsupervised classification? Sorry? But then it comes back through the window. I mean, you throw it out of the door, but it comes back through the window because at some point you will have to. The advantage is actually another one, which relates to spectral classes. What do I get when I use unsupervised classification? I get anonymous classes. What are these anonymous classes? They are groups of samples, group of classification units, which are similar to each other. These are typically spectral classes, as written here. Okay. So the advantage is that this classification will never try to separate classes that are not separable. Okay, so if you use supervised classification and you teach your classifier to separate, to distinguish two information classes that are actually not separable because they correspond to the same spectral class, you will get random results. Okay, it will be the noise which will determine whether any classification unit will fall into pixel A, so into class A or into class B. You will get a lot of errors. This cannot happen, generally doesn't happen, in unsupervised classification. Because in this case, you naturally get a partition of the data set into spectral classes. Okay. Now, let's move on to the next step. Now we have defined what is the operation of classification. We have seen what you can, what are the features of the different strategies. Now we want to see the so-called classifier. So what is that we use in practice to do classification? Now, as I said, classification has been around for much longer than deep learning. Actually, deep learning itself has been around for very long. Deep learning was invented, learning, machines that could learn on the one side, and and algorithms that imitated the operation of the neurons have been around since the 60s. Okay, so it's nothing new. The reason why they can be used now is because now we have machines with sufficient computational power. In any case, if we narrow down our view to the Earth observation context, before deep learning approaches became mainstream, a number of classical, a number of known DL and known ML approaches were already there, had already been invented. And we see some here. We have this called, in terms of unsupervised classifiers, we have this called K-means. K-means is a great classic. K-means is a way to group vectors by similarity. In your case, these vectors are spectral vectors, are the numbers that you find when you pull a drawer out of the filing cabinet. Almost exhausted the time for the first hour. And the same applies for supervised classifier. We had the parallelepiped classifier, which was very simple, minimum distance classifier, maximum likelihood classifier. It is interesting to have a look at the maximum likelihood classifier because it's historically it is very important. The maximum likelihood classifier is a classifier which treats the input vector as a multivariate random variable and assumes that, let me say it in another way. I talked about spectral behavior, okay, spectral behavior of a certain class. We have seen at the beginning of the course, we have seen the spectral behavior of vegetation, for example, okay. If you take that as a description of how vegetation behaves, then that's the ideal response. When you consider remotely sensed data, when you consider a classification unit and the spectral response that was recorded there, you should not expect to see, even if it's vegetation, you should not expect to see exactly the same response. Why? For various reasons. The features of the sensor, the atmospheric conditions that may not have been fully corrected, the errors generated by the measurement process. Okay, so all these factors will contribute to kicking the recorded spectral response out of the standard ideal response. Right? Okay, but then at the same time, so I'm simplifying it a lot, but then at the same time, you can also assume that these disturbing factors will not be too strong. So you have to do with a random variable, okay, because you don't get a predetermined value. There are random disturbance factors, but this randomness will not destroy completely the information. And you can, because small perturbations will be likely, large perturbations will be less likely. So ultimately, what you can do is you can assume that you have a Gaussian probability density function for each of the classes, a Gaussian describing the probability of a certain sample to belong to a certain class, which increases as you get closer and closer to the ideal behavior. Does that make sense? So this is the ideal behavior. I know I won't get it, but I know that, or I can assume that the closer the unknown sample will fall to the ideal behavior, the more likely it is to belong to that class. I can still make mistakes, obviously, but as I said, this is for granted. I will always have mistakes. I'm just trying to make them as small as possible. And one way of making them as small as possible is this maximum likelihood, meaning that when you use a maximum likelihood classifier, you define a model for the probability distribution of samples to belong to a certain class, which is Gaussian, multivariate Gaussian. If you're using, for example, Sentinel-2 data, it will be a 13 variate vector, and so the Gaussian will be correspondingly a 13 variate Gaussian. Thank you. Okay, so, and this is, the interesting thing about this object is that although it's not exactly true that the behavior is Gaussian, but approximately it is. And there's a theorem which states that if you do actually have classes whose behavior, if you do actually have a Gaussian behavior for the classes that you are considering, so if it's true, should it be true that the likelihood goes like a Gaussian, then this is the ideal classifier. There's no way you can do better than this. Okay, there's a theorem, it has been demonstrated. The fact is, you almost never have an ideal Gaussian behavior. Okay, so that otherwise there would be no deep learning, nothing. It would be unbeatable. But this case doesn't happen very frequently. Okay, then these are the classics. Then, at some point, we started moving to a successive step of, how can I say, complexity, which is let me wrap up this. In all these cases, when you're using a supervised classification, you also need a training phase, which was called training at that time, and it remained with that name. And training in this context means that you have to determine the parameters of this Gaussian. So when you have a maximum likelihood classifier, you do training, where training doesn't mean showing samples. It means something much faster and simpler, which is you estimate the statistical parameters. So you assume it's a Gaussian, because that's the underlying assumption. You assume that the distribution of your samples is Gaussian. So you estimate the average, the mean value. You estimate the standard variation. And then you use these values to write into the classifier. End of training. Extremely simple. An interesting thing about this classifier is that since it's true, it's never rigorously true, but it's frequently approximately true that the distribution is Gaussian. So it can be fairly frequent. This type of classifier is a good choice. Okay. Obviously, you can't ask for perfect results, but if you want a simple approach to the problem of classification, this is good. Okay. Then, as I said, then we started, just let me say this couple of things, and then as the availability of computation power increased, then the research and the operativity started moving towards more refined approaches, which included machine learning and deep learning. Machine learning in general means that the algorithm learns increasingly from the samples that it is processing. Deep learning is the further step where you have neurons or neuron-like structures which are trained using the samples of the training set. Okay, so now I would stop here and have a brief break. That is right. It is now. Or no? Yes, 10 to 11. If you agree, let's have a short break, and then we will start the next lecture in about 10 minutes. Okay.